Okay, my name's Guerney Hunt. As it says up there, I'm from IBM Research. And this is joint work with a whole bunch of people in IBM, which I'm not going to try to list them all, but one of the senior software engineers is Ram Pai. He's down in our Linux technology system in Portland, Oregon, in that area, in Hillsborough, actually. So we're talking about Protected Execution Facility. Let's see if we can get this to work. There we go. So this tells you that there's a lot of people, and on the right here, this is something that we have to stick in everything we publish about it, which says that this capability was derived from a project that was sponsored by the Department of Homeland Security and the Canadian government and the Air Force Research Lab, and none of them have anything to do with what we're saying. But that's what we got to do. I think this probably tells you that I'm the one who's talking, and it's not an official statement of the IBM Corporation, but at the end, I'm going to give you a pointer to the hardware architecture document that is now public. So that is more of an official statement, but it probably says that we're not really guaranteeing we're going to do this yet, but even though we're talking about it in lots of places. This is the overview of my talk. I'm just going to talk a little bit about the problem, which all of you know, so I'll probably skip through that. Then I'll give you two versions of the architectural overview. Since I'm assuming that the audience here is not deeply steeped in power architecture, although I know that there's a few people out here who've done some things with power, I'm not going to go down into the bits and bytes. I have one foil on that. If you're interested in exactly what we're doing and how we change it, then there's a pointer to the document that you can get on the internet. So you would call this a trusted execution environment. And what we're trying to do is deliver this technology to power and OpenPower. And the important thing here is the bottom bullet. All the software, firmware, and tooling is open source and will be available on GitHub. Some of the changes have already been posted to GitHub. I need to point out here that this is for power, and all of the software in power, from the first instruction that's run by the SBE, which is an internal processor in the power chip, to the last instruction that's run before you transfer to the hard native booted kernel, all of that code is open source. There are no hidden processors in the power chip. Everything is open source. You can look at it, you can examine it, you can play with it, you can do whatever you want. Okay? So you guys know the security challenges. You understand what's going on with multi-clouds, multi-computers, with firmware attacks and all sorts of other things. And you understand how hard it is to make something secure, more so than most people. So what we're trying to do with Protected Execution Facility is introduce this concept of a secure virtual machine. We're trying to protect this secure virtual machine from attacks by other secure virtual machines. We're protecting the confidentiality and integrity of the SVM. We're integrating with trusted computing tooling. We're enabling secrets to be embedded inside of the SVM. We give you some tooling that will convert an existing VM into an SVM if it meets certain requirements. We're reducing the trusted computing base. We're relying on the open source ecosystem, so we're not inventing everything to enable this. We're doing this for Power and OpenPower, Power Linux and OpenPower, so it's running on Linux, and we're leveraging a bunch of other things. We don't have any limitation in the amount of protected memory at all that you can have, although it's not dynamically configurable. It has to be configured when you're booting the system and can't be changed unless you reboot it. And any existing application that you want to run or operating system how big or how small can run inside of an SVM. So this is the pictorial representation. You got this SVM there, and you've got Linux KVM as our hypervisor. You've got guest VMs. You've got the hypervisor. You've got this new thing we're introducing, which is both hardware and firmware, and we're protecting this thing from attacks by anybody. That's our objective. So, and we're gonna go, so creating it, you start with a regular normal SVM, you develop your application, you run some tooling that we're supplying, and you collect the security model for the initial release says that every machine has a public-private key pair. So you collect the public key of every machine you want to run it on, and the tooling confirms. The SVM, we're protecting the SVM when it's at rest, in transit, and executing. And part of the way we're doing it when it's at rest is we're assuming that you will have an encrypted file system. So your virtual machine will not be converted to an SVM unless the file system is encrypted. And so there are a bunch of different file system encryption technologies for Linux, and whichever one you choose, you inherit the vulnerabilities associated with that system. Some of them are better than others. I'm not going to talk about those right now. And then we build some integrity information in the tooling that's encrypted and protected. I'll talk about that more later. And then the output is the SVM. An SVM starts like a normal virtual machine. It's just a set of bits that you pass to the hypervisor and you say, run this. Very early on in the boot process, roughly towards the end of a module called prominent, it executes a new syscall that I'll talk about later. The syscall instruction has been in the architecture for a while, but there's a new variant of it that goes directly to this Ultravisor thing that I've hinted at. And then that Ultravisor picks the SVM up out of the VM up out of normal memory, moves it over into secure memory, does an integrity check on it, and if it passes the integrity check, it allows it to start executing as a secure virtual machine. When the secure virtual machine is executing, all interrupts go directly to the Ultravisor, which is this new level of microcode that I'll talk about in a minute. And the Ultravisor, if the Ultravisor can handle the interrupt directly, it does it. If all interrupts would mean even an H call. An H call is an interrupt. H call instruction causes an interrupt to the hypervisor. If you're a secure virtual machine, that interrupt gets passed to the Ultravisor. The Ultravisor protects your state, reflects to the hypervisor only that information that's required to service the interrupt. When it comes back, it does it in the reverse direction. So that was the high level. Let's get into the lower level. The first thing we did was, prior to this introduction, our processors had 3 states: hypervisor, OS, or operavisor, and problem. They now have 4 states. There's a higher privilege state called Ultravisor state that's another bit in the MSR. We divide the memory into normal memory and secure memory, and you can only reference secure memory if you're running in secure, and the only way you can be in secure mode is if you're placed there by the Ultravisor. So this is the high-level overview, sort of letting you know what we did. We have some non-volatile memory. We have a TPM, the private key that is used to decrypt the information necessary to make sure that an SVM is actually secure, is locked inside of the TVM and can't come out. So everything that everybody said about vulnerabilities associated with TPMs is not, I'm not trying to change that. This is just what we're using at this point in time. The protected execution facility includes some hardware changes in the CPU. And one of those changes is a partitioning of the memory into normal memory and secure memory. And then requiring what we call the Protected Execution Ultravisor, or Ultravisor for short. The only thing that's trusted in the system is the Protected Execution Ultravisor and the stuff below it. For those of you who may be familiar with power architecture, when you turn the power on, it comes up in secure mode, but not with. But there's a new control register, but not with setting that it'll be in secure mode forever. Basically, your host boot and your ski boot or OPA, whatever you want to call it, they run in secure. They run in secure mode, so they can set everything up. At the end of that, before ski boot finishes, it loads the Ultravisor, checks its signature, loads the Ultravisor we're using to secure and trusted boot. When the system goes back, when the Ultravisor returns to ski boot, it is no longer ski boot is no longer running in secure mode, and the rest of the boot process is done with ski boot in hypervisor mode. So we have a hypervisor, whatever hypervisor you want. We're using Linux KVM Linux KVM to build this, but you can put any hypervisor there you wanted. And then you have your secure VM preparation tool that you can use to make your secure VMs, and then you ask your hypervisor to execute it, and it works. Now we'll walk through it a section at a time. I think I said all of this. There really isn't any reason to walk through it again. So at the lowest level, as I said, the private key of the TPM remains in the TPM. The Ultravisor uses the TPM to get access to the symmetric key to protect the SVM, but the Ultravisor does not have a TPM driver. So you're saying, well, how do we talk to the TPM? The answer is we talk through the hypervisor. Well, how can you talk to the TPM through the hypervisor securely? The answer is that the TPM and the Ultravisor share a secret that's set up before the hypervisor boots. So anything that's critical to the TPM, all the information, it's done through what's called a secure session in the TPM. The TPM protocol checks the integrity of all commands and stuff, so you twiddle with it, you just get a denial of service attack, which we can't prevent in this architecture. But we can talk securely to the TPM. We can pass encrypted stuff to him and tell him to decrypt it for us. If the conditions are right, he'll decrypt it, and he'll send the response back to us encrypted, because we can both derive the same key, and then we get that response. So we do that. That's what we do. I've told you we separate memory into secure memory and normal memory. And I've told you that when a VM tries to make a transition, it only successfully transitions if as best as we can tell, it has not been tampered with. We have higher privilege than the Ultravisor. The hypervisor has to be para-virtualized to work with this. We've done that, and some of those changes are upstreamed in KVM already, or in Linux as well. And some are still in process. I have a page on that later on in the presentation. In our processors, there's a lot more registers in Power than the standard instruction registers, MSR, and stuff like that. The Protected Execution Ultravisor owns them all, because because some of those registers can be used to change the configuration of the machine. And the hypervisors that run on our platform sometimes have to touch other registers that are in the architecture, but they're not in the ISA. And so if he's going to touch any of those registers, he's got to ask the Ultravisor, and we've done a lot of work to look at. There's some code down in there that says what he's allowed to do and what he's not allowed to do, so that the security state can't be changed. I should say one other thing. One of the things, when we build our processors, there's lots of different components. There's like DMA, I/O, and all sorts of different subsystems in the processor chip. And one of the things we did was we walked through, for this initial release, we walked through every subsystem block that's in the silicon, and we looked at its function and what service it provides to the system, and we decided whether we could make it secure or not. And if we decided it could not be secure, it is prevented by the hardware from referencing secure memory. So we've done a lot of work to make sure that only the things that will align with our desire can actually physically reference secure memory. I'll talk about some of the implications of that in a bit. So the biggest change in the hypervisor, or a simple change in the hypervisor, is normally the hypervisor just executes an instruction to go back to when it wants to schedule a virtual machine. That we had to change it, add a couple of instructions, so it looks at something in the saved MSR register, and if it detects that it's going back to a secure virtual machine, instead of executing what's called an HRFID instruction, it has to execute an ultra call to say, start this thing. It's a 2 or 3 line change, but we had to do that. Okay. At the VM level, When we do this, you can run normal VMs and secure VMs on the same hardware. One of our design principles was we did not want to, because we don't know how many people are going to use this TEE, the goal was not to impact the performance of normal virtual machines with this hardware change. Okay, so the significant, this guy here, there's no console. You can't talk to him with a keyboard. There's no timer interrupt that will cause him to execute. The only thing he executes in response to is either an interrupt that happens when something secure is running or an ultra call. That's the only way you get to him. So that means that he never, if there's a normal virtual machine running on top of here, he never comes into play, which means that the overhead associated with this architecture is less than 2.5% and primarily occurs on boot when the platform is booting up and not in steady state at all for normal virtual machines. For secure virtual machines, it's going to vary a lot on your workload. So we create these things with new tooling. I told you that. Sorry, this is so repetitive. So some limitations. We're not going to support suspend, resume, migration, and overcommit of SVM memory or dedicated devices to SVM in the first release. All of these are things we're looking at. We're not supporting transaction memory, so that applications that use transaction memory in an SVM will not work. So that's about the only application restriction we have. Okay. So we have this thing we call the ESM operand. I told you we execute this ESM instruction. ESM stands for inner secure mode. And it has an operand, or a block of binary bits that go to it that are passed to the ultravisor to get the thing to shift over. So this is telling you what's in it. So the top three things, the purple, green, and gray thing, we call lockboxes. What those are is a symmetric key that protects the blue things encrypted with the public key of the machine it's going to run on. There's multiple ones because you can have as many as you want because you can authorize it for as many machines. Now this is an initial model. It's not necessarily the final model. The next block in here, the next stuff in here we call payload blobs. And the blue ones are all protected by this symmetric key. The red thing at the bottom is HMAC, so we can make sure that nobody's been twiddling the bits in the payload blobs. There's integrity information on the kernel, the initram FS, and the RTAS. Those are the three things that we have to verify have not been modified since the boot file system is encrypted already. What's also there in that next blob is the passphrase for the encrypted file system. So obviously one of the changes to the Linux kernel is if the kernel knows it's coming up inside of an SVM and it can tell, then instead of asking the operator for the passphrase for the file system, it asks the ultravisor, because that's the only person who has it. And the ultravisor will pass it back. We allow for the customer to include as much other data as they want encrypted by that symmetric key in blobs. And there's a call where they can say, well, give me what's in this one, give me what's in this one, give me what's in this one. That call goes to the ultravisor. The application gets it without talking to the hypervisor. The ultravisor asks the TPM to use the private key of the machine so that the ultravisor can decrypt it. If a PCR is not in the correct state, the TPM will not give the ultravisor access to the machine. We check. We are going back and forth on exactly what we want to check, but right now we use secure and trusted boot, and we don't check the firmware versions to make it easier to maintain it. But what we check is that the verification code is correct. We check that the hardware key hash is correct. We check that the facility is enabled and that secure boot is not disabled, and that and if that's all there, a password will be set on the key, and we will be able to get access to it and use it. The password is changed on the private key every time the machine boots. It's not a persistent item, but the password is passed to us by the firmware below the Ultravisor as the machine is coming up. So you can use two SVM formats. You can either stick your ESM operand in the file system of the virtual machine, or you can modify a Z image. Modifying a Z image is a little bit more complex. The file system of the virtual machine is a little easier. This just lets you know how, if you modified a Z image, you could have multiple Z image. Each of them could have an ESM operand. Grub will boot it just fine, and you'll get into where you want. If you stick it in a NITRAM FS, it still works. So we've gone over most of this, that you start as a normal virtual machine, etc. If your verification, if we check your integrity and you're okay, then you end up into secure mode. We look at the verification information. Well, this points out that the first thing the Ultravisor does is look through those blobs and see, can I decrypt the symmetric key? So the blob is really an index that indicates which public key was used and the encrypted symmetric key. So we look for a set of bits out of our public key. If we find that set of bits in one of those blobs, then we know we can decrypt it. We decrypt it. We pass it to the TPM. We get it, and we get it back. If we can't decrypt the symmetric key, your execution stops right there. It fails because we can't decrypt the verification information. So we use that verification information to verify the kernel, the NITRAM FS, and the RTAS. When that's done, we go into secure mode. When we get a symmetric key, when the file system asks us for the passphrase, we use that symmetric key to decrypt the passphrase and pass it back. If they ask for anything else, we use the same key for that and pass it back. Okay. So many of the required changes for this are in kernel 5.4. In particular, changes to enable normal virtual machines to switch to secure mode, changes to enable secure VM to share unprotected pages with the hypervisor, which I didn't talk about. The changes needed by VirtIO and VPA are necessary in this area. Para-virtualizing the hypervisor to work with the Ultravisors up there. Some new HCalls we defined. There's a proposal to enable the ESM operand to be added to the P-series Z image. There are some additional changes that we're working on. So we do not in the initial release dedicate hardware to a secure entity, because there's more hardware work that needs to be done if we want to do that. Some various ways to do things like that have been discussed in this conference already. But we do enable VirtIO. So all the VirtIO stuff works. We don't, there are proposals for security that say, well, if you're doing IO, we'll automatically do TLS for you. We don't do that. We say, at least initially, we say, if you're going to do a network session with somebody who's not somebody else across the network, you need to be responsible and use the right protocols. So that means that it's possible for somebody to bury something into a secure virtual machine and for it to communicate insecurely with some other party. There's a proposal from Red Hat to fix that, but that's not something that we're trying to fix with hardware, with a hardware change. I mean, the virtual machine will run, we'll convert it. So most people use TLS in their virtual machines. Similarly, what we did require was we required your disk to be encrypted. And so we're using the encrypted file system of encrypting of the disk. With regard to paging, we will allow overcommit of memory for SVMs. We're just not doing it on the first day out. That memory will be protected with something called AES IAPM, if you're familiar with it. IAPM stands for Integrity Aware Parallelizable Mode, which gives you confidentiality and integrity protection, and it prevents replay attacks and all sorts of other things replay attacks, shifting memory around, and all sorts of other things. And there's lots of papers, research papers out about it that you can find. I don't have any references in this conference, but you can ask us for some if you want. So in terms of the interfaces to the Ultravisor, these are the ones that are used by the Hypervisor, and those are the ones that are used by the SVM. Share page and unshare page. Share page says, give me some memory that you have to, if you can't share a page of your memory unencrypted with the Hypervisor, then you can't do any I/O. So that's why we have those two. This is your enter secure mode one, and I don't remember what that last one is right now. The rest of these are fairly obvious. So when you're paging in and paging out, the Hypervisor cannot actually read secure memory. So essentially what has to happen is when we're going to do memory overcommit, the Hypervisor has to say to us, I want to page out that page. So we will mark the page. The Hypervisor will think the page is in normal memory. We will mark the page. We will say, okay, we're taking that page out. We will encrypt the page in secure memory and move it to non-secure memory and tell the Hypervisor you can write it out. And when we're doing overcommit and the Hypervisor is paging in, he says, oh, here's a page. He reads the page off the disk. He passes it into the system. He passes it to us in normal memory. The Ultravisor copies the page over into secure memory and then does its decryption, integrity check, and all of that. The way we use IAPM is when a page, part of the key that determines the decryption of the key and integrity checking of the virtual machine's page includes the virtual machine address. So if the Hypervisor were to pick up a page and hand it back to us and say it was a different address, we would get a fault and we'll crash the virtual machine right then and there. So that's what we're doing there. All of these are implemented right now. As we push through to our tech preview, we might have to make another one. We had to add a few H calls into KVM. This is the one that we use to communicate with the TPM. The KVM is not used to talking to the TVM because they make a device /dev/tpmrm or /dev/tpmrm0 available to the virtual machine. We can't use that, so we say, send this bag of bits to the TPM and send the results back to us. That's basically the effect of this H call. So this is my one page on describing the hardware in a little bit more detail. And that is, I told you in the beginning the amount of secure memory is configurable, but it's configurable per boot. We took an unassigned bit in the MSR and call it the MSR sub-S bit. That bit tells us the hardware that you're running in secure mode and changes your privileges and stuff like that. The only one who can set that bit is the Ultravisor. We now say that there are 3 bits, supervisor, hypervisor, and privilege, determining the privilege of what's executing. And this little table here tells you if you're running secure, you can be in one of 3 states. If you're running normal, you can be in one of 4 states. These are 2 hypervisor states. One of them's, you're both in hypervisor mode there. We added some new registers. They're mostly here. SMF CTRL is the SMF control register. There's a bit in there that tells the system whether or not SMF is enabled. These UR registers and US registers are registers that are similar to registers that we have for hypervisor mode in Power, but these refer to Ultravisor mode. We added a new instruction, URFID, which is similar to HRFID that can only be executed by the Ultravisor, sorry. And I've told you these other 2 things. Now here, we published, the date on it is September 9th, 2019, so it's kind of fresh. It's called the Power 9 Processor Programming Model Bulletin. What it is, it's an RFC to the existing, Power 9 architecture. This is supposed to be a direct link to it, and this is an indirect link. It kicks you to the IBM portal for OpenPower, and you can look under the public documents tabs and find it there. On the second page of that document is that same government disclaimer that I put on the second page of this presentation, as well as some other things. Let's see. So that's sort of a picture we can use to represent the changes at a high level. We enable these secure virtual machines. We protect the SVM from the hypervisor and from other system systemware. We protect the hypervisor from the SVM. The reason that protection is done is because when you're running secure, the Ultravisor controls your page tables. So you can only reference the memory that the Ultravisor allows you to reference, which is also how we protect the hypervisor, because we don't map the hypervisor's page space into the page space of the virtual machine. You're protected at rest, in transit, and executing. You can embed secrets in the SVM if you wish to. The memory size limit is adjustable. You can't use all available memory because you have to leave some memory for the hypervisor. Otherwise, he can't work because he only runs in normal memory. But you can use all, if you wanted to, you can make all the memory secure up to that much, up to what's required by the hypervisor. We don't tell you where to draw that boundary. You don't have to change any application and recompile an application to run in a secure virtual machine. If you're going to build an OS, you have to throw in some new we put some new K-conf options in for Linux. The hypervisor must be virtualized. We're virtualizing Linux KVM as an example of what you have to do. All the calls and stuff that need to be used by any hypervisor are public or will be open source. We allow you to convert normal VMs into SVMs because it's easier to debug it when it's a normal VM than when it's a secure virtual machine. And again, all of the firmware associated with this, all of the tooling, everything that that IBM is doing with respect to this technology is either already open sourced or will be open sourced when it's available. The rest of this is the research division blowing its hat, I guess, since I'm working for research. This lower thing on the lower left is the project that was funded by the US and Canadian governments. This is the final report. The hardware that we're implementing is derived from that. If you want to find out details about what we recommended, it's there. The rest of these things are things that have been done by IBM Research over the last 10 years or so, different technologies we've developed for various types of security. The one on the top left is similar to what I'm talking about today, but implemented purely in software on IBM Linux 1, which is a Z platform. So are there any questions?
Thank you very much for this. This was really interesting. From a threat model perspective, you listed the system admin as something you're protecting the SVM from. I noticed that the memory itself isn't encrypted.
It is not hardware encrypted. It's encrypted. The secure memory is encrypted whenever it's made available to the hypervisor. In the initial platform, it's not encrypted by the hardware. It will be encrypted in a future platform.
Okay, so it eventually will be encrypted. And then, so secure memory, you said, can be accessed by an SVM or the Ultravisor. Is that, so it looked like that was a single bit in the MSR. How do you separate the separate SVMs to make sure that there's no attack where an SVM can read SVM memory from the other one? Is it just the page tables?
It's just the page table.
Just the page table.
Page table has been a relatively effective isolation mechanism for several years, assuming you can't get into the kernel. I didn't make the comment here, but the Ultravisor is orders of magnitude smaller than a hypervisor. Orders of magnitude, less than 100,000 lines of code.
Okay.
We wanted it to be less than, the research prototype was about 14,000 lines of code. But that's a research prototype. It's a little bit bigger now because we're making it into a full product.
And then one last question. So when you're unsealing the key for the VM, can the customer know that the measurements of the Ultravisor and the firmware and all the pieces in the boot chain are included in the TPM registers that you're sealed to?
Those measurements are all, the key is not sealed to those measurements, but you can use an attestation protocol with the TPM to get the measurements of the firmware on the system, so the customer can know that. A second thing we're looking at is there's a particular security model here, and we haven't either, the tech preview will be published with the security model I defined here, but we're actively in the process of debating the security model for the GA product for a lot of reasons, because we want to target this as cloud, and this model doesn't work very well for cloud.
That was kind of where I was going, yeah.
So one of the things that we're looking at, and remember, I'm talking, not the corporation. One of the things we're looking at is enabling the customer to specify in their ESM blob which PCRs they will accept. And if they do that, then if those PCRs don't match, their VM will never execute. And there's a lot of other things we're looking at. We don't allow, for those of you who are familiar with the TPM, we do not allow duplication of the public-private key pair from one machine to another machine, because the duplication protocol, though it's secure with some assumptions that could be violated by a hostile party and expose your secure entity. Another thing I should point out is that when I say I sell this guy a machine, he uses it for 5 or 10 years, and he sends it back to me, to IBM, and I resell it to you. The process we go through in our remanufacturing and reauthorizing of the machine will cause any existing public-private key pair to be unusable in the TPM. So the second person can't use the public-private key pair, has to be re-provisioned. The way we do that is we do not insert a public-private key pair into the TPM, because then somebody could know the private half. We tell TPM, give us a public-private key pair, so the re-provisioning of the machine causes a new one to be generated. We allow you to take, because everything is open source, we allow you to take control of all the firmware in your machine. To do that, you have to reinstall, you have to install your own hardware key hash and start signing all of your own firmware, which you can do. But our design is that the hardware key hash is part of what we check in order to release the public-private key pair. So if you take control of your firmware after people have built secure virtual machines from it, the ones that were built under the control of the previous person become unexecutable.
Okay. So my question is on how the process building the SVM image. So you need to have the public key of each of the platform, like which is you talk about, right? The public key that generated from the TPM to encrypt this shared secret key that to encrypt the image, right? So in the cloud environment, really is a scalability issue, right?
Yeah, I said that we were looking at a different security model, because the problem in the cloud provider is, do I want the public key? Do we want to force the cloud provider to manage a different public key for every piece of hardware we've got? Another potential alternative security model is to make the responsibility for putting the key shift the responsibility from the cloud provider to the customer. I'm not going to try to explain how that would work. You would still have a public-private key pair in the machine, but that key pair wouldn't be capable of decrypting the SVM, and the customer would run a different protocol to decide which machines in the cloud provider he wanted to authorize his equipment for, and only the machines authorized by the customer would be able to execute a secure virtual machine. So we're shifting the model. So we're going from one extreme to the other, and we're primarily working with various people trying to figure out what's the sweet spot here, what's the right model. Because we want to enable migration, and we're looking, we want to make sure that we want it to be able to fit nicely into deployment models that are used by customers today. We understand the challenges of this, but so we're saying, okay, let's get a tech preview out, let people play around with it, see what stinks, and then try to fix it before we GA.
So you were talking earlier about...
Who's talking? Oh, there you are.
So you were saying that there's a pre-shared key between the TPM and the Ultravisor, and you had to use the Hypervisor
Secret.
proxy,
Pre-shared secret.
right? And you talked a little bit about the provisioning. What is the mechanism by which the pre-shared secret is provisioned to the Ultravisor?
Okay, when the code for ski boot becomes open source, you'll see that when there's a thing called the wrapping key. It's might show up in this document. That's the public-private key that's sealed to the TPM and has a certain policy on it. And the policy says that it can only be used with a password. And the password can only be set at a certain point in the boot cycle. And that point is when ski boot is executing. It's called when you have platform auth, if you're a TPM guru. So we're trusting host boot, we're trusting the code that runs in the SBE, we're trusting host boot, we're trusting ski boot, and we're trusting the Ultravisor, and that's it. So every time you boot the machine, ski boot sets a random password, uses the random instructions, generates a random password that conforms to C string characteristics, and assigns it to the key. And then when it passes control to the Ultravisor to initialize itself, it passes that random password to the Ultravisor and erases it out of its memory. So we get the password from ski boot. So if the PCRs are correct when we go to start an SVM, then we can unlock, then the TPM will use the private key to decrypt for us. Is that enough information?
Having never seen the sequencing of ski boot and stuff like that, not quite, but you said, first I heard that there was a password-derived key, and then I heard that there's a random key generated each time.
There are two things. There are two things. There's a random public-private key that's generated. There's a way we do that. And that key is inside the TPM, and it's generated with a policy that says it cannot leave the TPM, and it can only be used if the correct password is passed in on the command. That's the policy associated with the public-private key pair that's used to decrypt the secrets. The public key you can get by just asking the TPM. Anybody who's running on the machine can ask, etc. But the private key will never be given out. So that's the public randomly generated public-private key pair. The second thing is that the policy associated with that key pair says it can only be used with a password. The password is not persistent in the memory of the machine. So the password is changed every time the machine boots. In the boot sequence, the password is generated by a piece of code that's called ski boot or Opal, depending on who you are, same code. And assigned, and it does an operation that generates the password associated with there's a way for it to tell the TPM to associate this password with the public-private key pair. The public-private key pair is persistent in the TPM, and there's a way in the operations, which I'm not going to try to describe here because I'm not that much of a TPM expert, to say, this is your new password. So Opal says, this is your new password, and then when it starts the Ultravisor, it gives the password to the Ultravisor. So when the Ultravisor goes to decrypt one of those blobs, let's say it finds its index in the lockbox, it says, oh, I can decrypt this one. It copies that blob out, it does a sequence of commands that I'm going to net out as the following. Here TPM is my blob, here TPM is the password, which is encrypted, because I'm passing it through the hypervisor. Please decrypt this blob with this password. So we initialize a secure session. I say, I want a secure session. I'm going to encrypt my input and output parameters. So TPM sets up a secure session. We happen to both know the password, so we can derive a session key from that initial random password. That's what's going on. So then we pass our command down with the encrypted data. The encrypted data on the request is only the password we're telling him to use to authorize decryption of the lockbox. The TPM gets because the lockbox is already encrypted, we don't have to encrypt it again. He gets the lockbox, he gets our encrypted password, he knows he has, and I'm doing a high-level description, not a operation-by-operation TPM description. He knows he has to decrypt the password with the session key to know what it is. He gets the decrypted password. If the password is correct, he says, oh, you're allowed to use it. But the policy says only if PCR6 is valid. So he checks PCR6. If he checks a couple of PCRs, if those PCRs are valid, then he will use that password. And he will do an operation that uses the private key to decrypt the blob, the encrypted symmetric key. He will get back the symmetric key. He will encrypt it with the session key and pass it back to the ultravisor, and we will get it and be able to use it.
Yeah, so I get then the high level. What I wasn't getting is you're basically saying the upfront, you're really just restricting the access to the TPM key to the ultravisor. Like that's what the first order password is about.
Right.
I was thinking you were doing just typical sealing to measurements.
No, we're restricting the access to use that key to the ultravisor because the whole thing's busted if anybody on the machine can use the key, right?
Right. All right, thanks.
Before we go to other questions, is it possible to have an architecture diagram up or navigate to the best part of this session?
Which one do you want? You want the overview?
Just some structural, yeah, just to give context.
Okay.
Does the hypervisor have access to the SVM's general purpose registers?
No.
Okay.
Okay, so I flew by this. I'm an SVM I'm running, or the SVM's running. It makes an H call, okay? An H call is where the SVM is asking the hypervisor to do some work. We're not rewriting the hypervisor, so the hypervisor is going to do work. So what happens is that H call goes directly to the ultravisor. Doesn't even pass through the hypervisor. Comes into the ultravisor says, oh, this is an H call. It says, oh, it's this H call. He goes to a routine for that H call. That routine saves every register in the SVM in state in secure memory, and all of the registers on the processor state in secure memory as well. And then we insert dummy state into all of the registers where we think we need to insert dummy state, except the registers required for the hypervisor to properly execute the H call. And I flew by the fact that there are buffers and things that they might be passed on an H call. All of that is done. This implementation requires bounce buffering between a secure virtual machine and a hypervisor, and that's taken care of as well. Okay.
That's great.
Hey, a little bit. Hi.
You're next.
Over here. Oh.
Go ahead.
Passing pages between the secure world and the non-secure. Well, whatever an SVM and a non-SVM. If I understand correctly, the idea for the future is to have physical DRAM be encrypted, right?
Yeah.
Okay, so if I want some page that can be used for communication between a given SVM and the outside world, it has to be probably not encrypted with that SVM page, right? So I need some mechanism to...
You've made an assumption about how the encryption is done.
Fair,
okay.
yeah.
So what you've assumed is that the encryption of the physical RAM is controlled by this CPU here. It could be, it may be affected by the CPU, but it might be done at the DRAM, at a chip between the DRAM and the system, in which case it would become orthogonal to this, and not even the ultravisor would know the key. But when the memory was brought into the CPU for reference, it would be decrypted automatically, transparently. That's one possible implementation. Another possible implementation is that we control the keys for the secure guys, and somebody else controls the keys for all the rest of the memory, independent. The main point is that if we do something like that, we have to make sure that we have the ability to say, instead of saying that this memory is shared between the SVM and the hypervisor unencrypted, what we're saying is this memory is shared between the SVM and the hypervisor without the protection of the encryption required by the SVM. There might be other encryption that's applied to it if it's out in main memory, but when it comes back into a cache and is referenceable by the hypervisor, that would be taken off by the hardware. Does that help?
Yes. You also would like different VMs to have different keys, right?
We can do that, yes. If we are not happy with purely relying on the Ultravisor's page table management, we will assign separate keys to each of the VMs. We can do that when we have the hardware. We don't, you can imagine as we're evolving this, there are lots of debates going on between different people who have to do different things. But that can be done, yes.
Yeah, because I'd like the ability for to be able to make reasonably strong guarantees that once a VM has been evicted, all of the secrets that may have been known by that VM can no longer be accessed by the
Well,
host.
right now what we do is we encrypt the VM's memory when it's visible to the hypervisor, and each VM's memory is encrypted with a different key. So that's what the Ultravisor does now, but that's not driven by hardware.
Okay, but that's only when you paged out, right?
Well, yes, it's when you page it out. We would like to we would actually like to not have the Ultravisor manage the page tables. So that's another debate. And so what that requires is doing a few things so that we can use the page tables managed by the hypervisor. But since we control everything, we have to be able to say whether a page is secure or not. And if a page is secure, then it would be encrypted. And if it's not secure, it would be unencrypted. It would be referenceable by the hypervisor. And if we have a mechanism to say that a normal page in a page table is secure, then if the hypervisor touches that page, an interrupt will occur, the Ultravisor or the hardware will encrypt it and make it available to the hypervisor transparently, and then we don't have to manage the page tables, but that's a separate issue. It's another alternative. But yes, we want to make sure whenever the hypervisor can see the memory, it's encrypted. Whenever it sees the memory of different virtual machines, that memory is encrypted under a different key than everybody else. We do have it is possible for two virtual SVMs to share a memory because they would share that memory under a key that neither one of them knows. We haven't enabled that in this prototype. In this design, but it's still possible. So yeah, when we clean up the SVM, we erase the key that governs the memory that's encrypted, so it's gone. But we also built into the Ultravisor that when memory is allocated to a secure virtual machine, we zero it.
Okay, and then when you page out memory, it sounded like you were like the liveness of the system guaranteed on the guest to encrypt it within its own SVM in order to pass it back to the hypervisor in order to allow it to be paged out?
No. When the memory gets paged out, the hypervisor says, I want to page this out. He says that to the Ultravisor. The Ultravisor says you want to page it out. The Ultravisor does the encryption, not the guest. And then he moves it over to normal memory, and then the hypervisor pages it out.
Cool.
By the way, the algorithm that we use, if you have 0 pages, if you encrypt a page of all zeros, it will never look the same in your lifetime. So somebody has the blue box. They had a question.
So back to TPM. So I was a little confused about the concept of when you first boot, you generate a random password, and merely by being the first to get there, you will later get access to the secrets. Is that one and the same as the platform auth that you're referring to? Is that random password?
Now, platform auth is a state that the system is in as it's booting up.
Okay.
It's in the TPM architecture. Mm-hmm. But I was giving you a technical detail that might have been confusing. Ignore platform auth. When the system is booting up, when it's first turned on, the TPM is in a state where a password can be assigned to the public-private key. That's the key thing.
So you don't need to have the previous password in order to set the
you do
correct
not
password.
need to have the previous password to change it.
So
But-
so you just have to be the first to execute.
You have to be the first. You have to be the first firmware on the machine executing. Yes.
Okay.
And because it is the first firmware on the machine that's doing it, it sets that password, flips off that capability, and it can't be changed until the next boot.
Okay. So there isn't any pre-shared secret or anything like that at the other side.
No, there's no secret in all the code is going to be open source, so we can't put a password in the code.
Right. No. Just hoping. And when you're trying to first seal or encrypt some secrets to TPM, are you locally doing any verification on the EK or the EK certificate or anything like that?
There
to make
are,
sure you're talking to a
there are
TPM?
certificates in the TPM. There's a manufacturing certificate from the TPM manufacturer, and there's a certificate in the TPM put there by IBM that says this is an IBM machine. It's a TPM that was installed in an IBM machine, et cetera. Now, IBM right now, in the way it builds its servers, is not trying to protect against physical attack, okay? Because they sell these things to people who put them on raised floors and who are basically trusting. It's not like we sell it to somebody with a soldering gun and stuff like that.
Okay.
And there's debates going on about that, but the reality is the TPM is on a pluggable card, and that has some exposures, but the way we're doing the policies, we're okay for now, we believe. Next question. Somebody, does anybody have the?
Is there a way for the SVM software to verify that it's been correctly bootstrapped into secure memory?
It will never execute if it's not in secure memory. So what do you mean by correctly bootstrapped?
I mean, suppose the hypervisor just doesn't make any of these ultra calls or...
Then it'll never get into secure memory. The hypervisor actually cannot put an SVM in secure memory.
Right,
Okay.
I misspoke then. So the SVM just trusts the hardware platform that...
The SVM puts
everything is
itself
fine.
into secure memory by executing the ESM call.
It
Okay.
executes ESM.
And that call
And
by
if
hardware
that
goes
returns-
directly here to the Ultravisor. All right? Hypervisor cannot stop it. All right. Now, remember that ESM blob?
Yep.
Wherever it is, in here someplace. Right there. Okay. This ESM blob is the operand the SVM has passed on its ESM call. If the hypervisor, and that's available to the hypervisor, guess what? If he twiddles with any of the bits in this thing, he's dead. If it doesn't integrity verify, it will never, even though, the first thing we do is move the whole thing into secure memory, then we check its integrity. If that integrity check fails, he doesn't start executing. He dies.
So what if an SVM tries to run on a hardware platform that doesn't support the ESM instruction and treats it as a no-op?
It will be a no-op, and he'll start executing, and he can look in he can actually look in, there's a MSR sub S bit in the MSR, and when the SVM is executing, actually he may not be able, there's a way for him to do it, to look and see that he's actually running secure. There's a debate. He can't see, what can he see? There is a way for him to, you want to know how he tells he's actually running secure. That's what
Right.
you want to know,
Yes.
right? I think can you move from MSR? I think you can run a little thing to look at the MSR and look at the bit. Or there's probably another way. But that is important that he can actually know. He can verify that he's running secure. If he's not, if he treats it as a no-op, yes, you can tell you're secure because the SVM kernel can tell that it's running secure. And because it has to know it's running secure because it has to use an ultra call to get the secret to decrypt its disk. So in particular, if you're running on a machine where this is not enabled and it's treated as a no-op and you keep running, all the ultra calls will fail, including the one that gives you the password for your disk. So your disk will never be decrypted, so you will crash fairly quickly. Okay, I mean, that's a rather hard crash, but you can't decrypt your disk, so you're down, you're dead. You're dead.
Okay. You can't decrypt...
Oh.
No.
So is there a replay protection on the encrypted memory?
Yes,
How?
AESI, APM. Well, the better answer is Merkle trees.
Okay. In I guess it's all in software. So my other question.
Well, we've done it in hardware before, but it's not in hard. We've done it. It can be done in either software or hardware. Right now, we're doing it in software.
So my other question, you talked about effectively a launch control policy for the Ultravisor based on TPM PCRs. How do you have plans for how you can forward rev your firmware, right? To make sure that you can continue to launch your Ultravisor and launch your SVMs after doing firmware
Okay,
upgrades?
so we don't actually do the Ultravisor doesn't start the Ultravisor. The way we're not doing PCR checks to determine whether or not to start the Ultravisor. The Ultravisor is in secure boot mode, so if it's not signed, it won't be loaded and it won't start. So all the initial firmware is signed. It's signed and measured, so the PCRs go into the TPM, but they don't determine the running of the Ultravisor itself. What a few PCRs do is determine whether or not the Ultravisor is allowed to actually decrypt secrets to start SVMs. So that's slightly different. It's launch control for the SVM, not the Ultravisor.
But the impact to my virtual machine is the same, right? I can't load my virtual machine if the PCRs don't line up, and every time I do a firmware upgrade, they're likely
no,
to change.
what I thought I said was we are not including the PCRs of the underlying firmware at this point in what's required to launch an SVM. Someone down here asked whether that was possible, and it is possible. We're considering it as an enhancement, but the way we're considering it is not by not making it part of the hardware, but making it part of the SVM. In other words, in this area, we're considering up in the very first blob, putting something that says, I only want to run if the PCRs are like this. And so we would leave it to the SVM operator to decide which level of firmware he accepts or doesn't accept. That's for people who are really paranoid.
Okay.
It's an option we're looking at for people who are really paranoid.
So the SVM operator would have to update that every
SVM
time.
creator.
Yeah.
And there's tooling to update this that we give to the SVM creator.
Okay, so yet another iteration of this attestation question. I understand if I have SVM running provisioned already, then if something tries to emulate it or make this call and no-op, I won't get my disk encryption passwords. So that's okay. But how can I provision that VM to be sure it's really provisioned into SVM, not a normal VM or some emulation or something like that?
Well, you have to do the ESM call. Once you do the ESM call, that makes you an SVM.
Okay, but what if I'm doing that over some network and how can I verify is that really ESM call and not some emulated ESM call in somewhere else?
There's a protocol you can run, and in fact you have to run, when you're given a public key by, say, a cloud provider. There's another tool we're giving you that you run, and that tool will go out and verify that the public key that you've been given is actually associated with a piece of IBM equipment that's capable of running SVMs. Because if you don't do that verification, you run into the issue you're talking about. It's a series of attestation protocols. And so rather than saying, oh, customer, write all this code, we're just going to write it for you. So you take the public key, dump it into this tool, and it comes back and says, oh, it's a real one or it's not. And if it's not, you don't ever use it.
Okay, so I do this workflow to verify during provisioning SVM, and then it's up to my SVM to verify to do all kind of other attestation with my services I need.
Yeah, we didn't want to. We're not trying to tell you the SVM how to communicate with other people and how to accept input. That's your job. You know what you want. You know, we're just making sure that you can put enough secrets in there that you can be confident that if it's running, you can have secure conversations with other parties.
Thank you.
Just a quick question about OpenPower plan on supporting Xen. Is there any, or it's dropped out?
I don't know if you're asking me if IBM's going to put Xen to OpenPower. Not as far as I know, but I'm not involved in that. I mean, there isn't any reason why Zen wouldn't run on OpenPower. It's just a variant of Linux. And, if you run it's just a variant, it's rather trivial to port stuff to OpenPower Luli. If you want to go to OpenPower Big Indian, that's your problem. But maybe, for those of you who aren't familiar, IBM's machines have traditionally been Big Indian. And Intel, AMD, and everybody else in the world is Little Indian. I think with Power 8, we put in the ability for Power 8 to run either Big Indian or Little Indian. Okay, and so our Power Linux boxes all run Little Indian. All the distros that support Power run in Little Indian, not in Big Indian. Just as a technical detail, all the firmware we write runs in Big Indian. Some things you can't change, but you can tell by the fact that it's out there running and people are using it. The hardware doesn't have a problem shifting between the two, and the firmware doesn't have a problem. Most of the firmware that we write for the machine, the majority of it runs at boot and is never run. There's a small amount of it, like the Ultravisor now, which is new, and some other stuff that lies around after the boot process.
But my question was more, how do we start up the support of Xen for OpenPower?
Well, first of all, you have to be able to get the hardware. Somebody has to be able to get the hardware, and I'm not authorized to tell you how to get it. But you can talk to IBM if you want. It's actually for sale now. I didn't say that, but if you buy certain pieces of hardware from IBM or one of its OpenPower vendors, then this is there. If you wanted to start early, you would have to talk to us to find out. Let's see, who is it? Somebody mentioned them earlier. Raptor. Raptor makes, you did. Raptor makes boards with OpenPower, and more than likely, I haven't talked to them. Some of their boards actually have this facility in it. So you would have to get a Raptor platform.
Is there a possibility of joint effort from OpenPower and the developers? And you know where I'm going with that?
Yes, I know where you're going, but I'm in the research division. I'm not in the product division, and the Linux technology system is part of the product division. So I don't make commitments for them. You could explore that. I don't know, who would you talk to? There's no names in this presentation. There's beyond mine. You have to play by the rules when you're doing something like this. There's a guy by the name of Dimitris Penderakis. He was the PI on this government project, so you can find his name by following this link. Okay. He is the CTO for Security for Power. That's a discussion you should have with him.
Perfect. Thank you.
Sorry, just one quick comment on the Zen topic. For those who don't know, IBM was an early participant in Zen, and so for the first few years of Zen, I think there was even a PowerPC port out there somewhere. And then IBM went down the KVM route and now owns Red Hat. But there are
the PowerPC port is open source, so it's there. It's still available, but it hasn't followed the tree.
Yeah, and some people who have gone down the KVM route are now coming back to Zen for at least for specific use cases. So there's hope for large scale.
So have you considered, the disk is encrypted, but the kernel and initramfs and all those things are only integrity protected, not encrypted. Right. Have you considered a system where you have just a small bootloader that's going to run that instruction that moves you into secure mode and actually keep the kernel and everything encrypted? Because I worry that there's potentially some things in the kernel you might want to protect.
Yes, we have considered that. I can't comment on whether it'll be that way at the beginning.
You can create exec, right?
Sure, but to your point about whether you know your thing is running in a secure place, if you keep it encrypted and you know it can never be decrypted unless it's in the correct hardware, then you can't emulate it because you'll never have the decrypted kernel to emulate in the first place.
Right. So yes, we can encrypt the kernel. We could just as easily. wherever that thing is. We could just as easily, right now we're checking the integrity of the kernel. If we think it's important, we can change that to decrypt and then check integrity. Because all the code is there. It's just a matter of where do you apply it.
Well, but right now you're doing it from within the kernel. You're calling the instruction to move to secure mode, and you'd have to do that somewhat earlier if you can't read the kernel.
Let's see.
You'd have to do it in a bootloader or something.
We would have to change things because right now we actually start the kernel in normal mode through prominent, which I think is the first code that runs. And then at the end of prominent, you do the instruction. So we would have to change the kernel so prominent was unencrypted and the rest of it was encrypted, and a couple of other. I mean, it's not impossible, but we could do that.
Just a small stub that's unencrypted.
Yeah.
You can run this integrity protected kernel that will.
You can simply run this kernel that is integrity protected and have a script in Tramfest that asks for a passphrase that is encrypted in this blob and load another kernel and kexec into that encrypted kernel, right?
Sure.
Yeah, you can do that too.
Quick question on the paging here. So the hypervisor or the operating system can ask the secure VM, hey, I would like to page that out.
No, he has asked the ultravisor.
Okay, it asks the ultravisor, hey, I want to page that out. And later the secure VM tries to exit the page. I get some kind of page fault. And
what happens is he asks the ultravisor he wants to, when we get to overcommit, tech preview, no overcommit. But when we get to overcommit, he asks the ultravisor and says, I want to page this page out. The ultravisor controls the page tables. The ultravisor marks the page table. The page is invalid, encrypts it in secure memory, moves it to a place in normal memory, and says you can page it out.
Yes, and then when the VM tries to exit the page, that has to be paged out.
He'll get a page fault.
Yeah.
The page fault will go to the ultravisor. The ultravisor will reflect the page fault to the hypervisor. The hypervisor will read the page back in to normal memory, but it's been encrypted. He will then go back to the ultravisor and say this page is available. The ultravisor will know that he's coming back because of a page fault. It'll move that encrypted blob from normal memory into secure memory, decrypt it at whatever location it is, fix the page tables. When it does that decryption, it does an integrity check with a Merkle tree and all that to make sure that nothing's been fiddled with and it hasn't been moved around and all of that. And then he goes back to the secure VM.
Okay, when I remember correctly, this is exactly the setup you have with the control channel attack on SGX that allows you to at least infer what's executing inside an enclave, right? Because I can see whether I page fault or not. So I can figure out, okay, which branch is taken. Is this part of the threat model of SVM, or just do they say, okay, well, if I want to run an SVM, I have to make sure that I don't have this kind of attacks possible on my.
Which kind of attack are you concerned about?
The control channel attack, right? So they have, for example, a branch on a page boundary.
So the control channel attack works by?
Yeah, so the basic idea is I can page out a page from enclave, and when there's code on that page, right? So and I have a branch, and one branch goes to that page, and another it doesn't. I can see whether a page fault occurs, what branch was executed, and when I know the code, I can figure out, okay, what was the data that this branch depended on, and so figure out what's happening in the enclave. That's the basic idea. You could say that this is not in the threat model. That I'm fine
I'm not
with
sure
that.
that's a threat, but it's something we certainly will be looking at. So yeah, our pages are 64K. So we don't have quite the same. Some of the, for example, we all know about the cache timing attacks that were discovered in the early 2000s about how you could derive cryptographic keys using a cache timing attack on a unsuspecting entity sharing the same machine. And that was discovered on Intel architecture, which has 64-byte caches. Well, we did some analysis and discovered that it was significantly harder on Power, which has 128-byte cache lines, and impossible on Z, which has 256-byte cache lines. So some of these attacks, I'm not saying that you can't do it, but some of these attacks are much more architecturally dependent than we think. So we have to look not only what is the attack, but what features of the architecture is it exploiting to make it viable. Because our pages are so large that the branches across pages can be very, very small or non-existent in many applications, in which case it wouldn't work at all.
Okay, thank you.
I have two more questions. Yeah.
Oh, over here.
So the first question is there any limitations on how many instances of SVM can run on the platform?
The physical memory you've bought from IBM.
Okay. That's good. So second is, what is the performance, how many, seconds delay of, causing the VM to be launched because of this SAM process?
What's the overhead of a launch?
Yeah.
I haven't measured it on the code that's in development. In the research prototype, it was less than 10%.
Less than 10%? Oh, okay.
Most of the overhead occurred at boot time, and it was less than 10%. I'm not sure where we are right now with the product version.
Okay, all right, thanks.
Hey, over here again. If you want the hypervisor to actually be untrusted but provide device model emulation to the guest, then you need to carefully control the ranges of the guest memory that are accessible from the hypervisor. So like your rings for network IO or block IO or whatever. I haven't seen a way that, is there part of the launch that says, hey, I'd like these ranges to be accessible by the hypervisor and these ranges not, or something similar to that?
Actually, none of the SVM memory is accessible by the hypervisor. What we do is we're using VirtIO. We're not, so that is a form of device emulation. So we have a set of bounce buffers that are fixed range, and that's the only thing the hypervisor can. And the way the I/O is done is we use Are you familiar with the Linux kernel?
Yeah.
So we use HMM. We use HMM to do because it has all this bounce buffering support for graphics adapters, and we've modified that slightly so that it does the bounce buffering back and forth between the SVM and the hypervisor.
Can I grow the size of that bounce buffer at runtime?
That's a detail I don't know. I think it's gonna. I don't know the answer to that.
Okay, that's something that we would definitely want from a. Well, I don't know. Cubes is one example of a potential application, because if you want to add additional untrusted VMs behind a VM and add like dynamically hot plug network interfaces, then you want that capability.
Each VM has its own bounce buffer that's separate from everybody else. So every time you start a new VM, you're getting a bounce buffer. I thought, can I grow my own VM's bounce buffer? Was the question you were asking?
Yes, that is one. Because if I want to dynamically, for example, dynamically hot plug network interfaces, I don't want to have to multiplex them all into the same ring. I would like to have those appear separately.
If you want to dynamically hot plug network hardware?
A VirtIO interface, for example, yeah. Or add a disk, for example, or
we don't support in the first release physically assigning hardware to a secure entity. You can only do VirtIO.
Right. I do. I'm not talking about physical hardware. I do mean hot plugging more additional virtual interfaces.
Probably if you hot plug a virtual device, you'll get a buffer associated with it. With that device, I'm pretty sure, but I haven't looked into that. But that's an interesting question. I'll be asking. I mean, the reason I'm here is to get questions like this. Okay. Anyone else? I guess we got them all.